In this section, we are going to learn about rotational kinematics, angular momentum, and rotational kinetic energy. When a rigid object rotates, every point in the body moves in a circular path around a line called the axis of rotation, which cuts through the center of mass. When an object rotates, its radius will sweep a certain angle. This is called the angular displacement. We can also calculate the length of this segment, which is the tangential displacement. The angular displacement is measured in radians, tangential displacement is measured in meters. There is an easy way to convert between the angular and the tangential displacement. And if necessary, we can convert radians into degrees as well. Just like linear velocity is change in displacement over time, angular velocity, omega, is changing angular displacement over time. We can replace angular displacement with tangential displacement, which is delta S over R multiplied with T in this case. We can find that the delta S over time is equal to another velocity, which is tangential velocity divided by r. Therefore, tangential velocity is equal to r times omega in this case. Tangential velocity is measured in meters per second, and the angular velocity is measured in radians per seconds. Just like changing linear velocity is linear acceleration, changing angular velocity is angular acceleration. Angular acceleration is shown with the letter alpha, and it is measured in radians per second squared. And as we can see, we can replace the angular velocity with its tangential counterpart, and we find a relationship between tangential acceleration and the angular one. In summary, this is the relationship between tangential and angular values. Here is the list of equations and symbols for rotational and linear kinematics. Let's not forget the distance or displacement is equal to average velocity times the time equation. Similarly, we can use this lifesaver equation in rotational motion. The displacement, the angular displacement, is equal to average rotational velocity times the time. I suggest you should stop the video here and record all these equations in your list of equations. Here is an example problem. The turntable of a record player rotates initially at a rate of 33 revolutions per minute and takes 20 seconds to come to rest. Find its angular acceleration and angular displacement. Now let's have a list of givens like we normally do. So we have an original angular velocity, omega original, is 33 revolution per minute, and the time it takes for it to come to 0 is 20 seconds. Now, revolution per minute is not our standard unit for angular velocity, so we need to convert it to radians per seconds. So, first of all, is 2 pi makes 1 revolution, and in 1 minute we have 60 seconds. So with the dimensional analysis, we have the minutes and the revolutions cancelled out. This gives us 66 pi over 60. Doing a quick calculation using the calculator, we find that is 3.46 radians per second. Now let's solve for the angular acceleration alpha and the angular displacement theta. So acceleration is equal to change in velocity over time. This means final minus original velocity divided by the time, 0 minus 3.46 divided by 20. This should give me a negative, checking out the calculator, 0.17 radians per second squared. So that is my acceleration. Now let's find the angular displacement. Now there are several options here. I can use the angular displacement is equal to original velocity times the time plus 1/2 acceleration t squared. Well, that's definitely an option, but there's a better way to go around it. I'm going to use the average velocity. So the displacement is equal to average angular velocity times the time. So the average velocity is the velocity plus the original over 2 times the time. So this gives me 3.46 plus 0 over 2 times 20, and this gives me finally an angular displacement of 34.6 radians. Alright, so this is an example of how to use the kinematics equations when it comes to rotation then. Let's remember Newton's second law of motion. We know that net force is equal to ma. So force is directly related with inertia and acceleration then, and mass is a measure of inertia. So similarly, instead of force in the rotational equivalent, we use torque, and rotational inertia times rotational acceleration give us another equation for torque then. So torque is equal to I alpha. Let's make sure this looks more like an I. And now this means we have another equation for torque. So torque is equal to I alpha, in addition to the torque is equal to L cross F then. So we have two ways of calculating torque. And now angular momentum. Remember linear momentum, the definition. Momentum is inertia in motion, the quantity of motion. And the equation was P equal to mv. So momentum is equal to inertia times the linear velocity. So similarly, angular momentum can be described as moment of inertia times angular velocity then. This time our symbol for angular momentum is capital L, and I stands for moment of inertia like we know, and omega is for angular velocity. Now we can write this in terms of tangential values as well. So we know that for a small object, when the radius is much smaller than the axis of rotation, we have a general equation I equal to mr squared, and omega is equal to tangential velocity divided by r. So putting this all together, we have I omega can be put together like mr squared times tangential velocity over r. So I omega becomes mv r then. So for small particles, we can write L as mv tangential times r. We know that momentum is conserved when no outside forces acting on the system. Similarly, angular momentum is conserved when there are no outside torques are acting. We can write this equation as initial momentum L initial equal to final momentum L final, and we know that L equal to I omega, so our equation goes I omega original equal to I omega final. And again, for small particles and for tangential velocities, you can rewrite this as mvr initial equal to mvr final. In this example, we have a carousel free to rotate about its center on frictionless bearings, so there are no outside forces acting, and it's rotate about its axis. So the angular speed originally is 3.14 radians per second, and the original moment of inertia is 125 kilogram meter squared then. And a person suddenly jumps in to the edge of the carousel, so it makes the final radius 1.5 meters, and an additional mass just added to it is 40 kilogram. We need to find the final angular speed of the carousel. So in that case, the person acts like a small object with radius much smaller than the distance from the axis of rotation, and we can say that momentum original is equal to momentum final because there are no outside forces. So we know that I original omega original equal to I final omega final. So I need to find out what would be the final moment of inertia. Well, the moment of inertia for the person is going to be equal to mr squared. This is going to give me 40 times 1.5 squared. Using the calculator, I can see that this gives me 90 kilogram meter squared. Now, this is not the final momentum yet because this is just the additional momentum. So the final, I'm sorry, not momentum, the final moment of inertia. So the final moment of inertia would be the original one plus the person on it. So this gives me 125 plus 90, 215 kilogram meter squared. So this is the final moment of inertia then. We can see here conceptually that when the original momentum when the momentum is conserved and the original moment of inertia is relatively small and the final moment of inertia gets larger, in order to satisfy this equation, the final velocity must get smaller. So let's just plug in numbers and see this as well. So this means we have 125 multiplied with 3.14 equal to 215 multiplied with the value of final angular velocity. So using the calculator, I can find that the final angular velocity is 1.83 radians per second. As expected, it is less than the original angular velocity. Which wins the race, the solid cylinder or a hoop? We already know it must be the solid cylinder, but by how far? So, in order to solve a problem like this, we need to use conservation of mechanical energy. And we know that there are two types of energies involved in the mechanical energy, potential and kinetic energies. This time, however, the object is not just sliding, but also rotating. This means it has two types of kinetic energies. So, the first kind of kinetic energy is the translational or tangential kinetic energy, has the regular equation as we know it, 1/2 mv squared. And because of its rotation, it has rotational kinetic energy, which is equivalent 1/2. Instead of mass, we are going to use the equivalent for mass, which is moment of inertia, and the angular velocity squared. So, moment of inertia for the cylinder is given as 1/2 mr squared on a table, and moment of inertia for the hoop is given as mr squared only. So let's go ahead and write down the conservation of mechanical energy equation for the cylinder first, and mechanical energy original for the cylinder is equal to mechanical energy final for the cylinder. So at the top of the ramp we have potential energy due to gravity, but we have no forms of kinetic energies, so that will just be 0. And at the bottom of the ramp we don't have any potential energies, but we have kinetic energy for tangential motion and also for the rotation. So moving on, we have mgh equal to 1/2 mv tangential squared plus 1/2 I omega squared. Let's convert this angular velocity into its tangential form, because we know that omega is equal to tangential velocity over r. So putting it in its place, this part of the equation becomes 1/2 I v tangential squared over r squared. So putting it all together, I have mgh equal to, in 1/2 parentheses, let's say, m plus I over r squared and v tangential squared. Solving this for the tangential velocity, I get 2 mgh over m plus I over r squared. Now, I started solving this for the cylinder, but then this equation will be no different for the hoop. So this is my equation. All I need to do is plug in the values for the moment of inertia, and that should be it. So velocity here then for the hoop first, let's say, would be, their masses are the same, their r's are the same, so 2 times mgh m plus mr squared over r squared. Judging by here, what do you think the effect of having a different mass or even a different radius? It seems like no effect after all. So this becomes here 2gh over 2. So this gives me root gh for the hoop. And similarly for the cylinder, let's plug in all the values. 2 mgh divided by m plus 1/2 mr squared over r squared. Well, this part just becomes 1/3 over 2. All the masses do cancel, r's cancel, and I end up with 4/3 gh. This means velocity of the cylinder to hoop is equal to root 4/3, cylinder being the faster one. So again, seen from the equation for velocity, as long as you have the same shape, no matter what the mass or the radius, the tangential velocity at the bottom of the ramp must be the same. And this is all about rotational motion. Thank you for listening. We are going to solve more problems at school. Don't forget to take your homework quiz. Bye.